about pulse or window basis function. So let's consider the range of interest of domain size from 0 to 1. And we divide this region into n+1 equal subintervals, subdomains. So width of them will be hx. And then they also centered about the point xm, which we define as this, right? So m spans 1, 2, 3, and we have these subsections. And this is example for the case of n equal to 4. Also, Windows function, which is non-zero or only one of subinterval, is centered about xm, is defined as p. So p x minus xm. Basically, it's, you can see it's one in this subdomain regions, and it's 0 elsewhere. And then a linear combination of pulse functions according to this formula can be used. And just as a step or staircase approximation of this function. So you can see here is some kind of function, and then if we use these 4 regions, then we can have them approximated with these steps. We also can note that pulse functions are terminal in nature because they do not overlap with each other. Right? You can see that each of them in 1 on the interval of subdomain and 0 outside, so they do not overlap. And a pulse function can be differentiated only once. So because of it, it can be employed to approximate a function that is to be differentiable twice. Next, we talk about triangular basis functions. And the triangular functions or piecewise linear functions can be differentiated twice. So they define it by this expression, right? Or you can see the representation on this plot. Again, for the case of n equal to 4. Plot this each function is here. So linear combination of these functions give a piecewise linear approximation shown like these triangles. So these triangular functions are pretty simple because of the linear variations and resulting in integrability. And we also know that triangular functions consist of 2 connected subdomains, and 2 basis functions span a subdomain, right? And you can see, so if this subdomain, then you have these 2 span functions, or each function spans 2 subdomains. And the partial overlap between them makes triangular function non-orthogonal, right? Obviously, because they overlap. This is what we call non-orthogonal. So we can define the element size x by this expression, and then some of the commonly occurs math operations with triangular functions are the following. Again, we can differentiate it twice. This will be expression defined through delta functions. We can integrate this product of these two functions over some several subdomains. Then again, we know the expression, and we also can integrate the step function and triangular function in over a region, so we can have expression for this as well. So next we can also have spline basis functions, and in this case, spline of the order of n has polynomial degree n-1, and the order 0 denotes Dirac delta function, and the order 1 denotes pulse function, and the order 2 triangular function, and so on. So the order 3 spline function is called a quadratic spline. And it is continuous and has a continuous first derivative, and it's smaller than triangular function. So this is how we define quadratic spline. And this is example of function for x minus x2 up. And we can see that each spline function spans 3 subintervals. And 3 basis functions span each subdomain, right? So you can see tendency, right? When we increase order, we need to spend more subdomains, but we also have a high order of integrals being possible. So of differentiation order.